Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
The last talk in this session will be, again, on really important experimental design issues. It's presented by Johan Uganda, who is a postdoc at MSR and heading off to Stanford next year. And he's going to talk about some work he did at Facebook, looking at trying to design randomized experiments in cases where manipulating one observer may have spillover effects to others. And I think Ido will talk about some of that related ideas in the session on computational social science.
Thanks to the organizers. So I'm going to start with, when you're considering a complicated problem, you should always take the simpler version and make sure everybody is on that page. So A/B testing is randomized trials in an online setting. So you're trying to sell a flag, and you're interested in, you have this debate among engineers and designers that maybe the buy button should be green or yellow. And so you take a big population of users, and you flip a coin, and you give some of those users the version with the green buy button, some of them the version with the yellow buy button, and then you measure the purchase rate, and you put error bars on it, and you decide whether you want to move forward from that sort of data-driven decision-making approach. So this gets a lot more complicated in social networks, where you have all these different users, and you're running you're variously modifying their web experience via various experiments on either the layout or actual sort of under-the-hood algorithms that are doing ranking. And when you sort of assign these types of treatments to the users via flipping coins, let's take a really egregious or very complex example. You want to launch a new video chat feature on a site like Facebook. The problem with running an A/B test of video chat in this scenario is that you're then going to sort of, if you're going to try and measure the behavior of the users that have video chat versus the behavior of the users that don't have video chat, you have users that have video chat but have no one to talk to. So it's very important that you respect the social nature of the product change that you're trying to launch in these types of contexts. And ideally, there's sort of this fundamental problem of causal inference that has come up earlier, that you have these two kind of universes that you would like to compare, the version where nobody has video chat and the version where everyone has video chat. But you can't observe both of these at the same time, so you need to do some version of counterfactual reasoning. And maybe you're interested in the average treatment effect, which is what is the average time on site in this world versus the average time on site in the other world. And you can't really get that without kind of having access to different universes. So this is a sort of ubiquitous problem in lots of social web, social media contexts. You're doing product changes in something like Skype, or you're changing pricing plans in cell phone networks like Orange. You are affecting social product design in products like Skype, Foursquare, LinkedIn, people you may know, ranking algorithms. You have market mechanisms like the ad auction problem that Leon was talking about. You have Airbnb has inventory problems. Odesk is a labor market with similar inventory problems when they run experiments. And then in Facebook and Twitter, you have the newsfeed algorithms actually have huge spillover effects where if you improve somebody's newsfeed, you improve their engagement, they end up producing more content, and you end up actually seeing effects of the treatment on a user on their friends. So these are all kind of various versions of sort of spillover effects in experimentation problems in online settings. So I want to talk now for a few slides about the mechanisms that one can think about in these types of settings. So we're going to look at this kind of panel view where Y is the responses at time t and sort of stacked in time, and Z is the treatment of some intervention that we're considering. And this is a very, very small version of Facebook. And if we have this person here in the middle, we could say that, OK, here's something that's maybe reasonable. We're concerned that the treatment of the person's response depends upon their treatment and also the treatment of their friends. So in order to appreciate video chat, you need your friends to have video chat. Now, this is a simplification because really a lot of these types of problems flow through behavior. So you're actually oftentimes not responding to your friend's treatment, but you're responding to your friend's behavior, which leads to long-range dependence, which means that it's no longer, after any amount of time, it's no longer just about your friend's behavior, it's about the behavior of people several steps away from you and potentially the whole network, and you're back to this problem that you only have one network. And these two settings, where when you're sort of willing to view things as there's a treatment interference versus a behavior interference, are quite different beasts, where there's sort of more possibility of success in the treatment scenario than in the behavior scenario. So here, you still need to model some version of the human behavior of what is it that affects your behavior. Is it, do all your friends need to have video chat? Do some of your friends need to have video chat? But in this setting, you need to sort of model contagion in really complicated ways in terms of product adoption. Here, if you're willing to make some assumptions, you can get unbiased estimators. Here, you're wrestling a lot more with bias variance trade-offs. And to give sort of just a pointer to the flavor of some of the more technical version or contents of some of this work that I've been doing, in this setting, if you're willing to make sort of monotone treatment of assumptions, you can start to bound the bias and variance. If you're willing to assume that when everybody gets this product, they only increase their adoption. If they go in different ways, then variously the arithmetic becomes a lot more, or math becomes a lot more complicated. But I'm mostly going to talk about this context as an approximation of this context today. But I also have work on this problem explicitly. So there's a subtitle on this talk which is about design and analysis, which are these two opportunities to kind of get somewhere on this problem. If we have this network, as I hinted at before, one of the problems is that this person here doesn't have anyone to talk to. So one approach would be to say, OK, let's focus on the users who are surrounded. Let's do IID coin flipping. Let's focus on the users where they have the product and all their friends have the product. But the problem with that is that when we did this coin flip on this network, the only people who ended up having all their friends also having the same product as them, sort of properly in treatment in the sense that they have video chat and all their friends have video chat, and this person's in control and everybody they know is in control, is that these are the really low degree users. These are the users that only have one friend. So you're going to end up, if you go down this road naively, you're going to end up making decisions based on people who don't have any friends. And that's not a great way to sort of update, to choose the direction of your enterprise if you're a company like Facebook or any other social product. The other side of this is that you say, OK, well, I know how to solve that problem. I know how to cut graphs. So you say, OK, I'm going to flip these coins in a correlated way. And I'm going to say, OK, let's give treatment. Let's find a good graph cut. Let's flip the coin and give treatment to one half of the graph and control to the other half of the graph. But that's actually naive. That approach at face value is not a very good approach because you have really strong correlates of network structure. So a lot of the times, network structure follows from something like geography. And if you ran these experiments in the US, you would end up using something like the Mississippi River as your dividing line and find this great graph cut. And then you're going to be effectively looking at an average treatment effect where you're comparing the East Coast and the West Coast, or variously the West Coast and the East Coast. And you have a very huge bias in terms of the populations in treatment and control are very different. So the question is then how to cluster. How should you do this type of clustering if it seems like a good idea? So I'm going to, in order to talk about how analysis and design kind of make progress on this problem, I'm going to also lay out some of the basic notation. So if we have the treatment of a person, just sort of this index I, zi, is either 1 or 0 if they get a product or if they don't. And the response is that, for example, they either spend 60 minutes on the site a day or 45 minutes on the site a day. And then we have this sort of two universes that we can't observe quantity that we would ideally like to estimate, sort of an average treatment effect. And the A/B testing approach is that we do IID randomization, coin flipping, and we look at sort of the people who showed up when we flip these coins, the people who showed up with 1 and the people who showed up with 0. And we do inverse probability weighting on what we actually saw in treatment, what we actually saw in response. And we have this sort of this estimator of the average treatment effect. So that is no longer sort of an appropriate approach when you have these really complicated network effects. And the basic gist of the approach that I've been working on for this is that you say, well, let's actually, rather than having a person be in treatment when they have zi equals 1, let's look at which part of this 0, 1 vector are they responding as if they're in treatment. So for what sets in the 0, 1 sort of vector of all the possible ways you can assign your friends, are you responding as if everybody was in 0? Oh, I flipped these, sorry. And what instances of the 0, 1 of the assignment vector are you responding as if everybody was in control? And this is sort of, the natural version of this is to say, well, it's when all your friends are in treatment and you're in treatment, or all your friends are in control and you're in control. But there's choices there, and there's different ways you can approach that problem based on how you think the behavior goes. For example, if one of your friends has a highly infectious disease, that is very significant if you're looking at an epidemiological context. It's not just about, all your friends don't have to have a very infectious disease for you to be worried about hanging out with them. So the question is then sort of how does the behavior becomes a very important part of sort of approaching this problem and performing these estimations. Now, simply speaking, once you have made this decision of what you think is a good approximation of when somebody's in treatment, when they're network exposed to treatment in the language we use, you're just changing the estimation problem to saying, okay, I'm going to pay attention to them when when z fell in that set of vectors that they are sort of approximately network exposed, and then I need to compute the probability of z being in that set. So what's the probability of me having more than 80% of my friends treated, or having more than 80% of my friends in control? Computing those probabilities is a tricky part of this problem that I'm sort of giving a forward pointer to. But essentially, that's the whole meat of trying to look at these experiments when you're on networks, where you're interested in not just your own treatment, but other people's treatments, and then understanding what these probabilities are under more complex clusterings where you're not just doing IID randomization. So I was alluding to this concept of kind of network exposure, where really, normally we have treatment and control, and you're in treatment if you're treated, and you're in control if you're in control, or in the control condition. Being in control is something else. So this concept of being sort of network exposed to a treatment or network exposed to control, two basic versions is that your full neighborhood exposure is when you're exposed and all your friends are exposed. Sort of a fractional version of it is you're exposed and 80% of your friends are exposed. There's much more complicated exposure conditions that you can come up with and are, I think, very interesting to analyze, but are only more difficult than some of these more basic versions that we have been able to make progress on. For example, this person here has 2 of their 3 friends in the treatment condition. So you say, okay, most of their friends have video chat. That's great. But the problem you could think with this is that, well, but one of their friends doesn't satisfy this condition. They are only half of that person's friends have the video chat. So even though this person is sort of 66% sort of exposed to the treatment, this person is much less exposed. And is that person really going to adopt the whole video chat product because that person did? And actually, this maps into sort of understanding what the probability that somebody's in the k-core of a graph, and fractional k-cores for heterogeneous degree graphs and things like that. And so understanding what the probability of that happening is sort of this interesting discrete probability problem that comes up for trying to understand these types of experiments. So that's how you can analyze. Now the question is, okay, so how do you design with respect to the fact that you're looking to surround people and understand sort of that probability of you being network exposed? You want to make that as large as possible. How do you design for that? So here's a really good approach. Use New Zealand. And this is actually how a lot of companies solve this problem. It is, yeah. So it's English speaking. It has a pretty good graph cut. Its media doesn't talk too much to the US media. But you do get sort of in the tech-savvy news, you get headlines on TechCrunch like, oh, reports coming out of New Zealand that there's a change in the sort of layout of something definitely come up. Because this is a really hard problem to solve. And it's sort of, the generalization of this, though, is that, hey, actually, geography is a pretty good embedding of a large-scale social network. And variously, how can you sort of cluster this graph at a fine level, and at what level should you cluster the graph? Should you use countries? Should you use cities? Should you use high schools? Should you use pairs of friends to cluster? Where, but like at the two extremes, you have IID randomization, which is a factor 2 approximation to max cut. So you're cutting as a lot of edges. And at the other end, you have sort of the min cut, which is sort of the Atlantic Ocean. And where between those two extremes should you actually run your randomization is sort of one of the key problems in this design space. That on the one hand, you have you want to surround people. On the other hand, you have geographic correlates and other attribute correlates.
You may also have different effects for people who have long-term connections and people who have short-term connections. So if you decide to randomize
based on geography, yeah. So, and actually, you might want to find something that's orthogonal to geography because you're concerned about that. Or as soon as you start using geography, you also start introducing things like the latency to servers are very different. And if you're using European users in one case, you might only be seeing the effect of the fact that their connection to the servers are slower. And there's, yeah. So geography is a good starting point, but the better version is to use various graph clustering techniques that can do things like go against geography. Absolutely. But roughly speaking, once we have these types of clusters, in this approach, we're forming the clusters, and then we're flipping the coin of for the whole cluster at once. And then it's this very tractable problem of asking, OK, this individual, this was the small network. We ended up with 4 clusters. What's the probability that all their friends got assigned? And that's just sort of p to the number of clusters they're connected to, if they're asking for everybody. If you're asking questions, what's the probability that 80% of this person's friends got assigned, then it's this dynamic programming problem that you can solve without any major difficulties, even at scale, because it parallelizes across just the local neighborhoods of the entire graph. And then you say, OK, rather than using geography, can we use more advanced, highly scalable graph clustering techniques? And this is actually the approach. This is how I came into the problem, because that's something that I have worked on a lot before for sort of infrastructural challenges at Facebook and other things like that. So you have sort of label propagation and label propagation with constraints. You have sort of large-scale streaming algorithms. These are all great approaches to clustering really, really large graphs, sort of the really, really, really large graphs context. Another thing that's highly scalable that we analyze in some of the sort of theoretical aspects of this work is just using kind of basically epsilon nets or 2 or 3 nets, clustering the graph greedily. And if you make some restricted growth assumptions, diving into, again, technical literature, you can bound the variance of the estimators under that assumption, because if you use 3-net clustering, you can guarantee that people aren't touching too many clusters, independent of their degree. So that's very useful. I think that one of the things that I think is really interesting here is that there's a huge literature on community detection and graph clustering that has had a slight identity crisis over the last few years of what is the actual objective. As people got better and better at this, people started wondering, OK, well, in a lot of these settings, so what is a community, et cetera. For me, an interesting sort of large-scale project is to ask, how do these different clustering algorithms work in experimental settings of sort of applying community detection in experimental design of these highly clustered experiments. And it also kind of plugs into the large-scale framework. The way that I like to think about this at a high level is the whole process of running an experimental network is to say, OK, step 1, create a social network with 1.5 billion users. But sort of, you have some graph that you're handed, and then you have this design opportunity to sort of decide how you do the assignment. Do you do it IID, or how do you, most generally, how do you correlate assignment across the graph? The subset of correlation structures that I've been working with is how to do partitioning and then flip, make assignments sort of one partition at a time. But most generally, you could look at other correlations. And then you sort of run the world, the outcome generation process where people behave. And this is a process that is very complicated. And then after that, you try and discern who was really exposed based on how your design came out, and look at their responses and try and understand what would happen if you turned on the A for the whole graph or turned on B for the whole graph. And various results boil down to reducing the bias, and in the work that I've been doing on this problem, boil down to reducing the bias and the variance. So I'm gonna close with an example, sort of a case study on something that I worked on while at Facebook, which is In the status update prompts on Facebook, there's this question of what's on your mind. It's been there for a while. And on Thanksgiving in the year before I worked with Dean on this, Dean Eccles at Facebook and Brian Carr also, Dean had said on Thanksgiving, he ran an experiment on Thanksgiving where he replaced it with, what are you thankful for? And he saw that a bunch of users, their news, lots of people, both in the treatment condition, so he flipped a coin, IID, and half of the US received what's on your mind, and half of the people in the US received what are you thankful for. And then he saw, both in the treatment condition and in the control condition, huge amounts of status updates about being really thankful. And the problem with this is that, well, were people in the control condition, was there a huge increase in how much they were talking about being thankful because of Thanksgiving? Or was it because their newsfeed was totally overblown by behavior from the other treatment condition? Because half of the US was being prompted to talk about being thankful. So he said, okay, can we somehow separate these two worlds where we create clusters of the US that receive what are you thankful for, and clusters of the US that receive what's on your mind, sort of as the control condition. And one of the tricky things about this problem in practice is that graphs like Facebook are very, very dense, or relatively speaking. So we were actually looking at the interference graph that we considered was just people who saw each other in newsfeed, not the full social network. So it's also a directed graph, and there's other things that's nice about that because there's asymmetries that you can look at specifically. Use some of these advanced algorithms to create a lot of clusters. Had this unique opportunity to be able to use p equals 0.5. Usually when you run experiments, you only get to sort of assign 1 or 2% to a treatment condition. But here we could really sort of go 50-50. And then look at how people responded to these two treatments as a function of how they were exposed. So we actually were interested in something more subtle than just the everything off, everything on condition, because Dean, who has studied pure effects variously in a lot of contexts, was interested in kind of a causal answer to some of these difficult questions. And we were looking at the difference between the direct effect of sort of asking the person what's on your mind, and the indirect effect, which is asking everyone else what's on their mind, or asking everyone else what are they thankful for. And then the two universes that I've been talking about for most of this talk are the two corners, but we were also interested in direct versus indirect effects. And running this clustering algorithm, if you were in the thankful case, most users out of this sort of top 10 newsfeed friend graph had, the y-axis is logarithmic. So most users had sort of the majority of their friends in thankful, and the people who are in control, the majority of users in control. Ideally, this graph would sort of look that if you're in control, all your friends are in control. If you're in treatment, all your friends are in treatment. But this just sort of goes to show that these graphs are hard to cluster, and you don't get there, but you still have 1 million people surrounded in both of the cases. So you have people in the corners, absolutely. And then you get, this was one of the versions of the results from this, which is sort of the y-axis is the probability of using thankful words in your slides, in your status update, and the x-axis is the number of peers that have been assigned, and the pink line is the thankful condition, and the black line is the control condition. And you see this strong direct effect and also sort of a weak indirect effect, where one of the difficulties with this, the size of the dots is the number of people in each of these cases. And one of the tricky things about this is actually there's computational difficulties on getting error bars on this graph that I could talk about at length, but I'm not going to. But I want to conclude with sort of an opportunities overview, because that's actually how I view this area right now. There's lots of opportunity to apply various graph clustering and community detection ideas to experimental design on networks. There's kind of statistical theory opportunities to understand and characterize bias, variance, trade-offs of these estimators. There's computational challenges on how to compute various exposure propensities and really their probabilities on these in these more complex exposure conditions, like what I talked about K-cores. And most generally, graphs are becoming increasingly important for the types of response that people have to the designs of social systems. And so how can we understand, sort of develop graph matching techniques for how people are responding similarly under more general views of how they are positioned with respect to a global treatment and things like that. So thank you, and questions.
So I guess this is a question about this Thanksgiving experiment, because that one, it seems like you can do these graph clustering techniques, but at the end of the day, there's very strong effects as to what occurs in your newsfeed.
Yeah.
And it seems like what you're gonna, taking the kind of econometrics, the stats out, you can do some sort of regression where you take some person, look at, say, the number of friends that posted in their feed, and look and see if, which question they were asked. And you're going to try to just do some regression and look at the coefficients and try to see which one's significant. And it seems like, in all these tests, like even if you split things in half, like you're going to do some regression, like is it really that they live in Mississippi or one side of the Mississippi River versus the other that's correcting for it? And what you could potentially try to do is look at the set of covariates you're going to correct for and cluster based on this sort of split on the things that you might think of as causal effects.
Yeah, absolutely. So I guess one of the ways that I view the clustering is that you're increasing the kind of the dispersion of how many peers were co-assigned, and sort of in the worst case where everybody has 100 friends, and you were do 50-50 clustering, you would get some sort of concentration where most people and very few people had anything other than between 45 and 55 kind of friends treated, and then your regression you'd have a hard time extrapolating out of that range when you're running kind of a regression on how many peers were assigned or something like that. So that in that sense, so I agree with the huge utility of all those methods. And in the application of those, I still think that these types of techniques are useful because they kind of put more people in more extreme conditions, but then you need to correct for the fact that high degree people are harder to surround on graphs and things like that. So you use some of these probability things to correct for that. But yeah, all those techniques are super useful.
Let's take one last quick question, and then we can take a break and talk about all the talks during that.
Can you go one slide back?
Yes. Yeah.
So you mentioned this effect is a strong effect between these two curves. Now, if you look at the numbers, it's 8.2% versus 7.6%. So can you explain why that's a strong effect? Some people might say it's no effect.
Yeah, sure. So that would be a matter of n is huge, and I'll speak briefly about the error bar question. So one claim would be, oh, but all the error bars here are huge, and all the error bars here are huge, and is this really an effect? The direct effect we've been able to clearly bound as very, very statistically significant. I mean, this is then your point is well taken that a lot of studies in social media have such a large n that they can claim statistical significance about any effect. And technically, we didn't pre-register our hypothesis with an outside agency, et cetera. So you're well-founded in having all sorts of questions about that. The harder error bar is actually the sort of across the different the different amounts of peers assigned, because you have to outer bound the variance, and those are conservative estimates, and we're concerned about that. But it's a sort of a valid claim that we're seeing ultimately what is a small effect. But it's definitely there.
So I guess my question is, for this type of network problems, is an effect of 0.4% important?
I mean, it could be 100 million people.
Yeah. So right, exactly. So if you look at the, not to reference it too loudly, but the emotional contagion study which was a newsfeed experiment, there the effect was very, very, very small, but they had sort of an n that was so large that, and part of the questions about why there was so much controversy over it was that the effect was so incredibly small that what are we actually concerned about? Within the category of kind of results that I've seen run on when experiments are done in newsfeed, I would consider this to be a fairly sizable effect. And it was about understanding sort of, here is an example, here's a kind of model problem for peer effects. Are people actually saying things based on what they're seeing in their newsfeed was the real question. So then it was really, it's the indirect effect that we were trying to understand. And that's why it's sort of the lack of, the difficulty of analyzing the error bars there is the more, there I don't have a solid claim that people are responding to what is in their newsfeed. But they are responding to this little prompt.
So let's thank Johan and the 3 earlier speakers. We have a break now until 11:20.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.